we've done the heavy lifting to describe how power series operate with respect to addition and multiplication, differentiation and anti-differentiation, we're finally ready to do some really interesting constructions with power series. And what we're going to do today is we're going to define the basic transcendental functions. So we're going to define the functions e to the z, cos z, and sine z, where z is a complex number. So e to the, for example, 4 plus 5i. Now e to the 4 is easy, e to the 5i, that's really hard to figure out what that means. Cosine is going to be even worse, right? What does the cosine of 3i even mean? These are some difficult questions, and it's really hard to make any sense out of things like sine and cosine as they apply to complex arguments. If you think about the unit circle definition of sine and cosine, the unit circle definition says, well, you should travel, if you want to know the cosine of theta, for example, then you should travel a distance of theta around counterclockwise the unit circle, and then you should figure out what this x value is, right? So this will be xy, and the x value of that is cosine of theta. Well, that unit circle definition of cosine is really not helpful if theta itself is a complex number, right? How can you go I units counterclockwise around the unit circle? I don't even know what that means. Equally useless would be the right angle. If you want the sine of theta, for example, then you can say the sine of theta is the opposite over the hypotenuse, and then, you know, that's a reasonable definition of the sine of an angle. But if the angle is 3 plus 4i, then I don't know how to draw a right triangle that has an angle of 90 degrees here and an angle of 3 plus 4i radians or degrees or anything at all. I don't know how to apply these definitions. And so in order to generalize the ideas of sine and cosine and also e to the z to a situation where the argument of these functions is allowed to be complex, we rely on a slightly less well-known computation for cos z and sine z for the real numbers, and for e to the z as well, the real valued Taylor series for those functions, which gives us power series expressions in the case of the real numbers. Now what we're going to do is we're going to just take these as given. We're not going to derive that these are the right power series. We're going to take them as given, and then we're going to do so many computations with them that we're able to say, yeah, those are describing the same functions we're familiar with. Those are really describing exactly the right functions. So if you don't already believe that these are the right power series for e to the z, for cos z, and for sine z, don't worry about that. We're going to just define interesting functions, and then we're going to prove so many interesting properties of these functions, particularly that the derivative of this one is itself. We're going to prove so many interesting properties that you'll come to believe that they must represent cos z and sine z, because what else could have all of those properties? So here we go. Here are the definitions of these things as power series. Notice these power series are centered at 0. So their convergence, their domain of convergence must be some ball of radius cap r at 0. We certainly hope that cap r, the radius of convergence, is not itself 0, because if it is, these aren't really very interesting functions. We'll see shortly that the radius of convergence of all of these is actually infinity. So here they are, their power series. They're centered at 0, so we don't have z minus a, we just have z. So they're centered at 0. And what we need to do first is prove that these power series do actually converge. So this is going to be a bit of a challenge. Well, it's easy for the exponential e to the z, but it's going to be a challenge for the cos z and the sine z. And let me point out why. They have alternating 0 terms. All the odd terms are 0 in this case. All the even terms are 0 in this case. This means when you apply the ratio test, it doesn't work. It doesn't work at all because every other term is 0. So some of the ratios are undefined because you have a non-zero thing divided by 0. And some of the ratios are defined but equal to 0 because you have 0 divided by something non-zero. And so the lim sup of this, it doesn't make any sense. Most of them are, half of them are not defined anyway. So the ratio test is completely not an option when it comes to figuring out the radius of convergence of cos z and sine z. But we're not going to worry about that first. The first thing we're going to worry about is finding the radius of convergence of e to the z, which is this function. If you don't believe that it really is the right formula for the number e, 2.71828182845 to the z, which is a complex number, don't worry about that. We'll prove that it has all the properties we really need in an exponential function in the upcoming lectures. So first, let's just try to demonstrate that this is a complex power series with a large radius of convergence by calculating its radius of convergence. So in order to calculate the radius of convergence, we need to use the Cauchy-Hadamard test, and that means we need the lim sup of the coefficient 1 over n factorial raised to the power 1 over n. Now, calculating 1 over n factorial to the 1 over n is a kind of an intimidating thing to do. It's possible. There are formulas that would help us, but it's much, much easier here to use the ratio test. So for the ratio test, what we're going to do is we're going to calculate the limit of an plus 1 over an modulus. The modulus won't matter in this case because all the coefficients are positive real numbers. So we're going to calculate this limit, and then the reciprocal of that limit will be the radius of convergence. And remember that we have special sort of conditions for that. If this limit gives you 0, then the radius of convergence is infinity, meaning it converges everywhere. And if this limit should give us infinity, that means, that's bad news, that means that the radius of convergence will actually be 0, which means that it converges only at the center of the convergence. And as a power series, it's basically useless. So let's calculate this limit using the ratio test, and well, for the ratio test, and we'll see what we get. A sub n plus 1 is the reciprocal of n plus 1 factorial, and a sub n is n factorial. And so flipping this fraction around, that's n factorial over n plus 1 factorial. And the all of the parts that make up n factorial are within this product here, which is n plus 1 factorial, and they will all cancel, and this gives us 1 over n. Now, I've written my work a little bit sloppily, but this is supposed to be a limit of that. So the limit of 1 over n plus 1 is equal to 0. Does that mean the radius of convergence is 0? No, that means the radius of convergence is infinite, which is very good news. That means it converges for all complex numbers z. So f of z equals e to the z, which is defined to be that, converges, so we should conclude here cap r is infinite. This converges for all z, which is good news. And it converges absolutely and uniformly on B0R for every R. It doesn't converge uniformly on the entire complex plane, but it does converge absolutely and uniformly, basically on every, well, on every bounded set, but in particular from the Cauchy-Hadamard test, on every ball of any given radius, finite radius, at the origin. So that's really good. That means that it is at least a function. Now, this proof has a convenient side effect, which will help us calculate the radii convergence of the trigonometric functions too. The side effect of this proof is that if I had been able to get that lim sup that I was a little intimidated by, the lim sup of 1 over n factorial to the 1 over n, if I had been able to do that, I would have gotten 0. And so let's point out that side effect. Why is this a side effect? Because when we proved the ratio test, what we proved was if you can calculate this limit, an plus 1 over an, then it must be equal to the lim sup of an to the 1 over n. And so the side effect of this proof is that the lim sup of the modulus an to the 1 over n, which to be specific is the lim sup of the modulus of 1 over n factorial to the 1 over n, is actually equal to 0. Because this limit is equal to 0, and when this limit is defined, we proved when we proved the ratio test, when this limit is defined, then it must agree with this lim sup. So this lim sup I really didn't want to calculate, but now as a side effect of the ratio test, I know that this lim sup is 0. So that's interesting. And we're going to use it shortly. So this gives us the radius of convergence for the exponential, and it gives us the radius of convergence. Well, it doesn't give us the radius of convergence of these. Now, as I mentioned, we cannot hope to use the ratio test on cosine, and we cannot hope to use it on sine. And the reason is because the terms are alternately 0, and so we simply can't calculate an plus 1 over an for half those values, and so we certainly can't calculate the limit. That means that we have no choice but to apply the Cauchy-Hadamard test for cosine. But it's even harder for cosine than it would be for the exponential, and I couldn't do it for the exponential. So how is that going to work? Well, we're going to use the side effect. So the radius of convergence of the cosine, and I think I'll do the cosine and skip the sine because it's basically the same thing. So the radius of convergence of this for cosine is going to be the lim sup, and that's the lim sup of over the values of n where n is even, and that's the lim sup of, let's see, well, this thing, right? So this is the formula for the nth coefficient, so that's minus 1 to the n over 2 times 1 over n factorial, and then take modulus of that and raise it to the 1 over n. So really, I mean, it's a little bit imprecise to say the lim sup where n is even. Really, it's the lim sup of a sequence which is equal to this when n is even and equal to 0 when n is odd. So to be perfectly precise here, it's the lim sup of an alternating thing which is equal to this when n is even and equal to 0 when n is odd. So can we calculate this? Well, I hope so. Now, notice here that I've got minus 1 to the n over 2, but I've got it inside a modulus sign, and so I don't need that. I can get rid of that. And I don't really even need the modulus sign at all because I know that n factorial is going to be a positive number, but let's just leave that. What's the radius of convergence for sine? So the radius of convergence for sine z is going to be another lim sup. It's going to be the lim sup of something that alternates according to this rule. It's going to be this same formula, 1 over n factorial modulus to the 1 over n, but if n is odd, and 0 if n is even. So I haven't calculated either one. I'm just keeping track of what needs to be calculated. Now, we're talking lim sups. And these sequences are, well, all of these sequences, because we've got the moduli, these are all only going to involve positive numbers. And so the lim sup could, in theory, be 0, but it can't be negative, for example, right? So we know that the lim sup is greater than or equal to 0. And so the lim sup is either greater than 0 because of this behavior, or is equal to 0. So, well, wait a minute. This thing that occurs on all the even terms for this sequence is exactly the same as the even terms of this, and we know the lim sup of that is 0. This thing, which is equal on the odd terms, is equal to the same, and we know the lim sup of that is 0. So if this lim sup is 0, then this is a lim sup of a whole bunch of positive values here, and if it still has a lim sup of 0, then that means that that's actually a limit, right? If the positive values have a lim sup of 0, then their limit certainly can't be lower than 0, so it must be equal to 0, and that means that this is actually a limit. So these things tend to 0. So what we've got here is we've got a sequence of values, and we know that the even values tend to 0. We know the odd values are 0. Here we know the odd values tend to 0, and the even values are 0. So what else is there to prove? This lim sup must be actually equal to a limit, and it must be 0. So let me erase this and say this limit must be 0, and this limit must be 0, because it's an interleaved, each one of them is an interleaved sequence. We know that half of the sequence, the evens versus the odds, half of the sequence is tending towards 0 because of this, and we know that the other half is actually equal to 0. And so we know that this lim sup is 0 in each case. And that means that the radius of convergence for cosine and the radius of convergence of sine are both happily infinite. So here I'm just going to say r equals infinity for cosine, r equals infinity for sine. So that demonstrates that e to the z and cos z and sine z, by means of this formula, are functions defined on the entire complex plane. Moreover, because they're given by power series and they have infinite radius of convergence, they have derivatives, they have antiderivatives, and those derivatives and antiderivatives are given by term differentiation. And when we do that, we know that the derivatives and antiderivatives are equally convergent on the entire complex plane. So we can calculate the derivatives and just using these power series expansions for these functions. And that's what we're going to do shortly. We're also going to prove lots of interrelating properties between e to the z, cos z, and sine z. And it really is a beautiful story how these functions interoperate. For the real values of z, the exponential function and the sine and cosine functions, they feel so very different, like they don't have anything to do with each other. I mean, exponential obeys this nice differential equation, which is order 1. These trig functions obey order 2 equations. These things are bounded. This is unbounded. They seem just so very different, and they describe different phenomena, right? This describes exponential growth, and this just describes oscillation. It just feels like they're so very different that they don't have anything to do with each other. In a complex plane, what we'll see is these functions are so similar, they almost are describing the very same phenomena. And so that, to me, it's really exciting that the complex plane gives us an opportunity to bring together the various roles of the different transcendental functions. And that's what we'll be proving soon.